Coming back, Kimoi Kemboi will tell us about exceptional collections on linear GIT quotients.
Okay, thank you for the introduction. So I'm interested broadly in derived categories of coherent sheaves. So this is a gadget you can associate to any variety X over K. And essentially, the objects of this category are complexes of sheaves on X, and they have a bounded coherent cohomology and modulo some relations. And so I'm interested in basically the relationships between this algebraic object and the geometry of X. And in particular, I'm interested in the structure of a full exceptional collection. So basically where this structure started from is this result of Bailinson from the 70s. And this is a pretty cool theorem. It says that the derived category of projective space can be described very concretely just from any list of n+1 such consecutive such line bundles. So like this. And what this means is that basically any complex in this category can be built in a canonical way if you allow taking direct sums or shifts of complexes, or sort of taking so-called cons of complexes. And just using these operations, you can build any complex here just from this finite list of line bundles. And in fact, more is true. So this first property is what I'll call generation. So this list of line bundles generates this derived category. And second, this if each such line bundle, when you just look at what subcategory generates with these operations, it's basically the complexes of bounded complexes of finite dimensional vector spaces over K. So in a sense, these are like very, very simple objects that you use to build everything. And third, that you can arrange this list in such a way that you have no, homes in this direction. So any homes from any such line bundles from the right to left vanishes. Okay. So this sort of structure, more generally for any X, any list of objects in the derived category that has these properties is called a full exceptional collection. So immediately from these properties, one can conclude that if you have a full exceptional collection, you get immediately a basis for the Grothendieck group of X. Basically, this tells you that the classes of the objects will span, and this will tell you that you do get in fact a basis. But in fact, this sort of structure is related to many sort of interesting questions relating to the geometry of X. Well, so one is this so-called Dubrovin's conjecture, and so Dubrovin used this collection on Pn to show that the big quantum cohomology of Pn is semi-simple. And so then conjectured that more generally, if you have a smooth projective toric Fano, that if you have having such a structure of a full exceptional collection is equivalent to this big quantum cohomology being semi-simple. Another sort of conjecture related to this is this Orlov's conjecture. Orlov's conjecture says that if X is smooth and projective, then having a full exceptional collection should imply that X is rational. So this is sort of a largely open kind of conjecture, but basically, it's sort of a guiding principle for trying to find examples of varieties where where you have a full exceptional collection. And this also sort of comes up in like homological mirror symmetry, where these, if you have a collection consisting of line bundles, then they should correspond to these so-called Landau-Ginzburg models. And so sort of these sort of questions and connections to the geometry of X motivates why we should try to find more examples of varieties that have this full exceptional collection. The problem is that there are not that many examples now. So immediately after this resultant PN, Kapranov showed that, you know, Grassmannians and quadrics have a collection like this consisting of vector bundles. And there are some more examples, sporadic examples for sort of other types of homogeneous varieties. But the only sort of full general class known is this type A situation. And then there are more examples in the toric case. So for toric Fano varieties with Picard rank less than 4, these are known to have full exceptional collections consisting of line bundles, and more generally for toric or bifos. So this is due to many people. Toric or bifos. This is due to Kawamata that they always have a full exceptional collection, but it's of some, you know, random objects of the category. So this is Kawamata. But most of the examples known sort of fall under the umbrella of linear GIT. And so really the question sort of I've been wanting or thinking about a lot is to just find general classes of linear GIT quotients for which you have the structure of a full exceptional collection. So what is the setup for linear GIT? Well, you have a linearly reducted group over K, and it's acting on a vector space X. And for GIT, you need some polarization. So you let L be a G equivalent line bundle on X. And so GIT produces for you some open subset of the semi-stable locus. And from this, you can construct, you know, the usual Mumford GIT quotient. The problem is that this is usually very singular, and one of the constraints of having such a structure is that your variety will need to be smooth and projective, so or smooth and proper. And so we, instead of looking at these usual GIT quotients, we consider instead the sort of stack quotient, and we make assumptions so that this is an orbifold stack quotient. And you have a map like this. When the action is free, it's an isomorphism. And so it's for this large class, this like class of GIT quotients that we ask this question. And so this is our question. And so for the rest of the talk, I just want to explain how one sort of approaches the question of finding this kind of structure for these kinds of quotient sets. But I'll pause for questions. Okay. All right. So the sort of idea, the sort of idea for finding this collections, it goes by this name, window categories. And the idea of window categories is as follows. So this GIT quotient sits as an open substack of the bigger stack. So you have this GIT quotient here. And the derived category of this stack quotient is just the equivariant derived category of X. And now X is just some vector space, so just the derived category of X is generated by just the structure sheet of X. And now the equivariant category will be just generated by just tautological vector bundles. So this is just a vector bundle of the same dimension as you, and you act like how you act is acted on by G. And here U is an irreducible representation of G. And so if you just look at this list of tautological vector bundles, they completely describe this derived category. So now the idea of window categories is that, well, this is open. And so if you restrict to the derived category of the semi-stable locus, this GIT quotient, this is essentially surjective. And now the goal, if you sort of imagine sort of this as the characters of these irreps are living in the weight space of your group, the idea is that you want to sort of find some kind of window, maybe some like bounded region in the weight space of your group. Let me call this region omega. So such that if I restrict this class to just those tautological vector bundles, so that the character here lies in this region omega. So I restrict to this OX times this U, such that character of U is in this omega. I want to find such omega so that if then I restrict to this smaller subcategory, we get an equivalence of categories first, and that 1 and 2, you can organize this list of tautological vector bundles so that you get a full exceptional collection. But the real hard part is in finding the appropriate window so that this is an equivalence. And sort of this circle of ideas, goes back to many people like Telemann and Harpan-Leisner, Vandenberg, Schwenko, and they use sort of these ideas to construct these regions for various classes of representations. And you construct this omega canonically, and you say what happens when you change your polarization, so that you get sort of canonical derived equivalences and things like that. And so in the case, Harpan-Leisner, Sam, they sort of construct these windows. In the case X is a self-dual, representation, and they construct canonical such windows and sort of deduce derived equivalences for generic GIT parameters. And it's this sort of ideas are used as well by Schwenko and Vandenberg to construct some non-commutative resolutions of quotients of GIT quotients. And so with Harpan-Leisner, we use this, we construct new windows where now we want to impose this second condition so that you get a full exceptional collection, and we produce sort of a large class when, say, G has rank 2, and sort of sporadic examples in higher rank. In higher rank. And so my sort of overall goal or that I'll be working towards over here is just finding sort of canonical windows and descriptions of wall crossing, of what happens when you cross walls in GIT of these windows for sort of large general classes of representations.
Questions?
You are always over an algebraically closed field.
Yes, of characteristic 0.
Ah.
Well, to produce windows for fully faithfulness here, you don't need to assume But for generation, it's sort of a combinatorial. You construct explicit complexes and compute cohomology with Borel-Veil, so you need to assume.
Can you tell some example in Hack 2 which you get?
Oh, so so Kapranov already showed for Grassmannians, but you could produce a new class with this technique. So this Grassmannian 2n as a GIT quotient, X is like 2 by n matrices. The semi-stable locus are full rank ones. If you look at the weight space, the sort of weights of this representation will be these are the weights of the standard representation of GL2, and you have n copies of them. And then the actual window that we construct sort of looks like a barrel, and we call it a barrel window. It sort of looks like this. And then you have some rule to determine how to eliminate the weights that lie on the boundary. And so you get sort of something that's like a minimal Lefschetz collection. If you use the one from Kapranov, uses a different window, and it uses stratification from Kempfness, and the window sort of looks like a square like this. And in fact, the Kapranov one is basically, yeah, if you write sort of the weights of the tautological representations appearing there, they do come from that Kempfness window.
In these more general cases, do you get a resolution of the diagonal like in the TN case?
No. So the idea, so you don't usually have resolutions of diagonal. They're very, very hard to construct. And so this is a different method that doesn't rely on using resolutions of diagonal.
So, okay. So if you randomly choose a window, do you get something nice corresponding to subsets of X?
No. This part here, the hard part. So it's essentially two different problems: fully faithfulness and essential surjectivity. Fully faithfulness has to do with finding weight criteria for vanishing of cohomology supported in the unstable locus. That's already a difficult problem, but you can, in some sense, if you have some way of writing a filtration, some like filtration of the unstable path, you can still construct some window. The problem is like, it also needs to give you essential selectivity, and sort of, it's kind of a miracle that they sort of happen to coincide.
What happens when X is not rational? Like which one of the conditions can you break?
Oh, this one?
Yeah.
Oh, there are many easy examples. So if, sorry,
Yeah, so is there a example where when you don't get a full exception collection?
Take
which one?
P3 and an elliptic curve inside, and then you blow up with that center. Then the blow up will have the collection of P3 and then some other piece corresponding to the direct category of this. And that is not an exception, doesn't have an exceptional thing.
Sorry, so what kind of object is X here? And is it like literally a fine space or?
Yeah, it's a vector space. Just think spec sim of a vector space.
Okay, so X is like just underlying a fine space of your representation.
Yes.
And self-dual in the sense of representations, or
What?
like what does self-dual mean?
It's self-dual as a representation. More generally, it's so-called quasi-symmetric, but it includes self-dual representations.
Okay, let's take speaker again.